So, in our Physics 132 class, we had a problem that I tossed out at you about a set of concentric spheres and using Gauss's law to find the electric field and some other things everywhere in space. When we did this, I went through it rather quickly, and I promised that I'd talk through it more slowly and maybe give you a little context on it. So here is that problem with some context. When it first came up, this semester, spring 2012, we hit it on day 17. So if you want to go look for the problem again in the context within the whole class, that's the file to look for, day 17. And this was the second day that we had spent talking about Gauss's law, solving for electric field. We had introduced Gauss's law even before that. Before we hit this specific problem, we already did a few pieces that are absolutely critical to solving this problem. When we first talked about Gauss's law and electric field, we saw that symmetry was a really important part, and I'm going to talk about that again when I get to actually doing this problem. We had solved for the electric field in and around a uniformly charged sphere, and we did that with Gauss's law. And we did that by invoking some symmetry, and we will use that in this problem. And also, we had discussed electric fields in conductors and why the electric field inside the body of the conductor is always zero as long as we're in equilibrium, which in this course, unless otherwise stated, we are in equilibrium. Just to review the definition, the electric flux, for which we use the Greek letter phi, is the integral on a surface of the electric field dotted with the surface vector. Those are both vectors, and there's a dot product. Gauss's law applies to closed surfaces, and it says that the total electric flux on a closed surface is equal to the enclosed charge over that constant epsilon naught, the permittivity of free space. It's that piece of the other way of writing Coulomb's constant. I note that this law applies everywhere. It's true everywhere, but it's not always useful. In this case, it is useful. So before getting to the big problem, let me review the answers we got for just looking at the uniform ball of charge. That is uniform density, uniform charge density on this 3D ball. The outside of the ball is spherically symmetric. Any surface outside contains the whole charge. Since it has the same symmetry as a point in space, everything looks exactly like a point in space from the outside. Gauss's law, remember, tells us as long as we know about the symmetry, it's what's inside that matters. So we get the same solution as for a point charge when I'm outside, when r is bigger than the radius of that ball, which I called A. Inside the spherical ball, we still have the same symmetry, so the field points out everywhere, but not all of the charge is enclosed. So as you move out to larger r, but you're still inside the ball, you don't necessarily have the 1 over r squared. In fact, what you find when you set up Gauss's law and do the really simple integral, which turns out to be just the volume of the whole thing, is that inside the ball, when r is less than the radius of the ball, you get k sub b and a function that's linear in r. Those are the things we had when we were ready to start this problem. So let's jump in and look at it. Here's the setup of the problem. I've got a uniformly charged insulating sphere, radius A, charge Q, just like that thing I just talked about. But now it's sitting at the center of a thick, uncharged, spherical conducting shell. Inner radius B, outer radius C. Thick shell made of conductor. In between, problem doesn't say, I assume vacuum. I want to find the surface charges induced on the inner and outer conducting surfaces, that is at r equals B and r equals A. We already know that for a conductor in equilibrium, any charge has to be on the surface. Just because there's no net charge, though, doesn't mean there can't be charges on the two surfaces. In particular, if this is a positive Q in the center, I expect negative charges to be attracted to it, positive charges repelled, so I expect some charge on the surface. Problem also asks me to find the electric field everywhere. And if I want to be picky about the language, it doesn't have a vector arrow on the E, so I only need to find the magnitude. But I know it always points out. So the first thing I do before I even start thinking about how to solve the problem is I label these regions 1, 2, 3, 4, so it's easier to talk about than saying R is less than A, R is between A and B, etc. Label the figure a little more. Turns out it's actually easier to get the electric field first. In fact, there are a few parts you know without doing any calculation. Probably the easiest one is that region 3. That's the body of a conductor. Within the body of a conductor, the electric field is always 0. That's a big part of the problem. Already done. Probably the next easy thing, since Gauss's law tells us it's what's inside that matters, is to look at that ball. Do we still have spherical symmetry? Well, yeah, I've got two concentric spheres. If so, it's what's inside that matters. We already used Gauss's law inside there. We know what the answer is, we just copy it over. It's K sub E times Q times R over A cubed. Just copied the result from before. I could look at either one next, but I want to look at region 4, the very outside of the whole problem. Well, I'm outside. I've got spherical symmetry, a known amount of charge. This is going to look like a point charge. K sub E times Q over R squared. The only region that might make you think, since we agreed that there might be a charge on surface at R equals B, is this region 2. But again, Gauss's law tells us that it's what's inside the surface that matters. So if I drew a Gaussian surface at a radius between A and B, the flux on it should only care about the charge on the ball. That means, again, this looks like a point charge. If it looks like a point charge, I copy down the solution for the point charge. I've just found the electric field everywhere. No real calculation for this. Problem also asks for induced surface charges. I need to think about Gauss's law. If I set up a Gaussian surface within the conductor, going all the way around, enclosing that ball on the inside and the inner surface, the surface at R equals B, well, the electric field in the conductor is 0. So the electric flux is going to be 0. If the electric flux is 0, that means the net charge enclosed is 0. I know the net charge on the ball is Q, so that means the net charge on the inner surface is minus Q. Not that hard. Outside the whole thing, well, there was no net charge on the conductor. And if there's minus Q on the inside, there must be plus Q on the outside. Have to be just a little bit careful because it asked about surface charge density, not net charge. So I divide by the areas of those spheres. At R equals B, I get negative Q over 4 pi B squared. And at R equals C, I get plus Q over 4 pi C squared. Again, the net charge, thinking about Gauss's law, no real calculation. The surface charge density, I divide by the surface area. If I plot that result, which I didn't ask for, but it's always nice to look at, you see the linear region. My picture got a little messed up, so there's a gap, but then the 1 over R squared fall off. The electric field goes to 0, rises again to 1 over R squared behavior. The discontinuity there is okay. because even though there's a finite surface charge density at r equals b and r equals c, the volume charge density on this infinitesimally thin surface would be infinite. So I don't have to worry about continuity of the electric field. If the volume charge density were always finite, I would have to watch out for that. So in a real world problem, there wouldn't be this complete discontinuity in the graph. It would fall off smoothly and rise smoothly, going a little further than what the problem asked for. So really we've got all the answers and a little bit more than it asked for. Problem probably wasn't quite as hard as you thought, but just to recap some of the things. First of all, we looked at solutions we already had. We had to check and make sure the symmetries allowed us to use the solutions we had. And we did a sense check at the end by graphing things. Hopefully that'll set you right on that problem or a lot of problems like it. Thanks.